Kalimera. Today we're going to be talking about geotechnical site characterization using shear wave velocity. Geotechnical site characterization is a first step in every civil engineering project. You need site-specific information on the soil and the rock. You need geoparameters in order to do a foundation analysis or decide if you need to use ground modification. You need to know that the ground is going to be stable during construction and is safe for the workers. And you'd also like to keep the lawyers at bay. And then I tell people, okay, stop, take a deep breath, count to 10, and look at the geomaterials that we're asked to do a characterization of. When you see them, you can notice that some are blue, some are tan, some are brown, green, white, red, all the colors of the rainbow. And one of our first tests is to do a grain size distribution, and we plot that on a logarithmic scale because we're going from microns to millimeters, centimeters to decameters, to meters to kilometers. The sizes are all over the place. Quote from Lord Kelvin, 1883, when you can measure what you were speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory. Maybe not the best, most uplifting message, but it's true. We're geoengineers. We need some numbers to quantify the materials that we're working with. And so normally we handle that through a number of different processes today. For thousands of years, we've been drilling boreholes and taking samples. That's one way to do it. It's the conventional method. And then we developed a number of in situ tests, penetrometers, probes, borehole devices, where we could measure something in the ground directly. And then we found out we could use the same equipment that our friends in geology developed for their purposes, geophysics. And so we have different types of advanced laboratory testing. If we bring samples back to the laboratory, we have triaxial, simple shear, consolidation, resonant column, direct shear. And I put together this slide that shows a variety of different, I call them toys that help you take the little specimens in the lab and twist them, and squish them, smush them, push water through them, and measure different parameters: permeability, shear strength, reconsolidation. And here's a selection of those. And I call those geotechnical engineers the lab rats, because they like to take the samples back to their laboratory where they have all the conveniences of being in a closed environment, fresh pot of coffee, maybe some pastries, alcohol. And yeah, it's just very convenient, but it's also very expensive. Each sample costs a lot of money to procure. We have to cut little specimens. Each test costs €300, €400, €500, maybe €1,000. They're expensive, and it's just a single point. So we developed a whole bunch of toys we could take out to the field. When I was growing up, I had a little sandbox. My parents gave me a bucket and a shovel, and I would fill up the bucket and dump it out. You know, after 2 or 3 weeks of that, it got kind of boring, so it was more fun to go across the street and play with the toys that your friend next door had. So we've come up with a whole variety of different types of in situ tests. They all have their own TLA, 3-letter acronym. And these are available for different purposes. Perhaps you want to measure K naught, shear strength. You'd like to measure the modulus of the ground. So you have to pick and choose which of these is going to work in the geology that you're exploring, which of these is going to give you the parameters that you need. And so that's a different kind of category of personality in geoengineering, and I call those people the field mouse. The field mouse because they like to go out in the field and push the probes into the ground and measure, get their numbers directly in the field. So I think it's a good idea to be a little bit of both today. A little bit lab rat, a little bit of field mouse. And if you're not familiar with these devices, we've produced this document that's published by the U.S. government. You can download it at the website there on the first line. It's a manual of subsurface investigation, and it's 372 pages. It's free. There's no charge to have that. We also have now geophysics methods. We have mechanical wave measurements, and we have electromagnetic waves. So those can be more or less distinguished by the frequency content. The mechanical waves are typically in the 1 hertz to 200 hertz. Electromagnetic waves are probably in the megahertz to gigahertz range. And those include, say, dielectric measurements, resistivity, electrical conductivity. You might know them as ground penetrating radar, electromagnetic conductivity, resistivity, and so forth. And those are very valuable. We just don't have time to talk about them all today. So instead, I'm going to concentrate on mechanical waves. These are all non-destructive, 10 to the minus 6 as a decimal. We could do them in boreholes, but we also have a family of non-invasive types where the sensors remain on the surface of the ground. And from those measurements, we can infer layering, elastic properties, stiffness, damping, and inclusion. So there's a number of different types of waves. Compression wave, P wave, that's the fastest wave. So on the oscilloscope screen, that's the easiest one to measure because of the first arrival. However, the shear wave is the second fastest wave, is also directional and polarized, and that's the most fundamental wave to geotechnique. We also have some hybrid waves. The Rayleigh wave, because the P wave and the S wave interact at the surface of a semi-infinite elastic half space, they interact and form a Rayleigh wave, also known as a surface wave. And that travels almost as fast as the shear wave velocity. So we've spent a lot of time using that technology to help us do non-invasive geophysics and determine a profile of shear wave velocity with depth. And I took this from Chris Clayton's Rankine lecture. He shows that, in fact, we have 3 different types of shear waves depending on the direction and the polarization. The movement in a shear wave, you have 3 principal stresses in a Cartesian coordinate system: sigma x, sigma y, sigma z. Well, one of those stresses is left out in a shear wave. It's only dependent on 2 of the 3 principal stresses. And so because of that, we have a VSHV wave. That's a typical crosshole type task. A VSHH, that's a special type of crosshole where we use a rotary torsional source. And then VSVH, which is downhole. And how do we measure that? Well, we have different types of equipment. Seismographs, spectrum analyzers. Way back before we had digital, we had pen plotters. We have particle velocity recorders, field oscilloscopes, and today you could even use your laptop computer because there's software. The computer's certainly fast enough to collect all that data, so with special software you can just use your laptop. One of the issues with compression wave is that water has a P wave velocity of 1,500 meters per second. Maybe it's also called the water density paradox because normally there's an increase of, say, density with increasing compression wave velocity, but then you have water, which sort of defies that law. And so you're not quite sure when you bounce waves into the ground, is it loose sand, medium sand, close to the P wave velocity of water, or dense sand? Same thing with clay. Is it soft clay, medium clay, or hard clay? And it's really not directly possible unless you have some ground truthing, say through a soil boring or a sand. So shear wave velocity, that's the point. Shear wave velocity is a fundamental measurement in solids, so you can use this on all of the geomaterials, and that's what makes it so valuable. You can do it on the smallest particles, which are colloids. You can do shear wave velocity measurements of clays, silts, sands, silty sands, mixed soil types, gravels, fractured rock, intact rock, gravels, mine tailings. Some people even use it on municipal solid waste, MSW. So it's just one of those, it's like one of the only tests that you can run on all the geomaterials, and I think that's what makes it so valuable. If we take the shear wave velocity and square it times the total mass density, then we have what's called G naught, G0. It used to be called G max. The dynamic shear modulus, it's all of those. And originally it was applied only to dynamic geotechnical problems, but then we figured out, hey, it also applies to static, monotonic loading. And so that, again, makes it even more valuable in that G0 is the beginning of every stress, strain, strength curve in soil and rock. So shear wave velocity is interesting also in that the shear wave velocity of water is 0. So there's no issue with any measurement as we had with the Hydro P earlier. It doesn't mean that the water table doesn't affect the reading, because water table will affect the effective stress in the ground, and that in turn will affect the magnitude of the shear wave velocity. It's just that it won't get in the way of our ability to measure the shear wave velocity. So I find it very, very useful. Here, the shear wave velocity of steel is about 3,100, 3,200 meters per second. And we have some intact rocks, some granites, that are actually even a little bit higher than that, maybe 3,400, 3,500 meters per second. So that's a pretty big range. On the other end of the spectrum might be peat, organic peat, with a shear wave velocity of only 10 to 20 meters per second. Artin, who was the 8th Athenian lecturer, put out a book, Rock Quality, Seismic Velocity, Attenuation, and Anisotropy. And he, in his book, I took these as excerpts right out of this document, the advantage of shear wave velocity compared to compression wave velocity. VS offers better resolution than VP in sediments. VS is not attenuated at the water table. It's little affected by the fluid saturation. And VS is better for detecting lithological changes in the ground. So let's go through some of the methods in case you're not familiar. Though some people, such as Professor Ken Stokey, University of Texas, Austin, he considers this the gold standard. Cross-hole seismic testing as ASTM D4428 We have a downhole hammer system. We can have the preferred method, which is 3 case boreholes with depth. It's very expensive, but we would use the interval between receiver 1 and receiver 2 to measure the travel times. The first borehole is used as a source hole. And then we have an optional method where we just use 2 boreholes. In that case, it's a direct arrival. In either case, you can determine P-wave velocity and S-wave velocity with depth. Here's the result. This is in Alberta. We have 2 formations. The upper firm sediments that are alluvial, and you can see the shear wave velocity is increasing from about 200 to maybe 350 meters down to meters per second down to about 12 meters depth, and then it's underlain by a very stiff to hard glacial clay till with a shear wave velocity of 450 meters per second. Now that's very expensive to install 3 case boreholes, so we came up with a less expensive, more economical downhole test. In the United States, we use ASTM standards D7400. We might put the source at the surface, a horizontal plank under the wheels of a vehicle, or just a piece of timber, and strike it on the left side and or the right side. And in that case, we're going to calculate the difference in the hypotenuse with depth. There's this tiny offset X that should also be less than, say, 1 meter. But the same principle, but as we go down the hole, we're generating a VH wave, and we can measure shear wave velocity. On the left side, it's true interval, where we use 2 set elevations of geophones. On the right-hand side, we just have 1 elevation of geophones, maybe biaxial geophone, and we look at the increment from 1 depth to the next, typically 1 meter depths. And here's a set where we have paired left and right strikes. The red strikes are shown by red lines. The blue lines are shown for the left strikes. And we can pick off either the first arrival or the first crossover. And we do that incrementally at 1 meter depth intervals. In this particular case, they're going down 31 meters in Virginia. And this is the profile that's interpreted. We have 2 formations here. The upper is a Holocene, young formation. Velocities are typically somewhere in the 200 to 250 range. And that's underlain at, say, 10 meters depth by an older Miocene age formation with, say, an average shear wave velocity of 350 meters per second. Here's a special test program by Ken Stokey, and in this case, they used 2 sources. One was a manual source to get them down maybe on the order of 50, 60 meters, and then below that they used a very high-powered source that's used in geological oil and gas exploration. And we essentially here we have both the P-wave velocity and the S-wave velocity together with depth. And if I take the reciprocal of the slope of the data, that would be the P-wave velocity and the S-wave velocity, respectively. And the profile looks like this. This is Stokey's interpretation. It's typical to show steps. I personally don't prefer the steps. I prefer just to show the midpoint as a single dot. But the convention is to show the steps at where they take the changes in the slopes. But in this case, you can see the 2 velocities with depth, and they're going down quite deep, 400 meters. There was a test program here in Greece, say over the last couple of decades. Pilolakis et al., Raptakis et al., and here they're showing shear wave velocity profile with depth at this particular site, the Eurosize test site. I'm sure you've covered that in previous There's different ways of processing the S-wave. You can use the first arrival, you can use the crossover method. Both of those require paired strikes, either left strike and right strike, and we superimpose those two. Or if we're doing crosshole tests, there's a down strike, there's an up strike, and we superimpose those to get the first arrival, first crossover. And then we realize that each of these wavelets, each of those wavelets at 1 meter depths is approximately 8,000 data points. Back 40 years ago when we came out with crosshole and downhole, we had analog signals, and we had to use this trick of the polarization. Fast forward to 2023, we can let the computer match, say, 2,000 points at the 1 meter depth with 2,000 points at the 2 meter depth, and match that with the 3 meter depth, and we can use thousands of data points because we could just use cross correlation. And my students would use MATLAB, and Dr. Mayne would probably revert to Excel, but you can do it on Excel as well. So we would just match each of those successive wavelets and get a profile. The other thing we got into was source. You can use a sledgehammer. It's very convenient. It's very inexpensive. Doesn't look very professional. Is that important? I think so. And the other thing is, I don't know how many golfers we have, but how often can you always hit a hole in one? Not very often. So each time you hit it with a sledgehammer, it's a different wavelength. They look different. So you can improve that by putting the sledgehammer on a pendulum, but it still doesn't look very good. So we spent 12 years developing auto sizes. This one used solenoid, so it has a left strike and right strike. We didn't develop Vertex. Sells a hydraulic one that's 18,000 euro. It's so heavy you have to mount it permanently on the belly of a big truck such as this. We developed pneumatic to get something more powerful, and we finally ended up with what we call roto auto size that we patented. It's just an electric motor with a gear on there, and one of the teeth is missing. And there's a spring on the hammer, so every time the wheel goes around once and it encounters the missing tooth, the spring goes pop, and that's how we generate wavelets. So we patented this. You can run it on AC or DC. It's portable. Even I can lift it. We've gone down 45 meters depth, and very interesting, we can generate shear waves every 1 second if we want to do that. Peter Robertson bought the last 7 that we made. He uses them in his work. If we're going very deep, we have suspension loggers, sometimes called P and S wave suspension logger, just to make the acronym bigger. The first version came out, the instrument itself is 7 meters long, so it's not that valuable for shallow shear wave velocity profile. It's better for very deep. And it was developed by the oil and gas industry, especially Oyo Geospace. So they can go on the order of kilometers deep. We had the opportunity to work with one in the New Madrid seismic zone, which is right in the middle of the United States. Our earthquakes are not very frequent there. Every 300 so years, we have 3 major earthquakes on the order of 7.6 to 8.1 magnitude. So in this case, we're going down almost 900 meters, and the P wave shown by blue squiggly lines, and the S wave is shown by purple squiggly lines. These are different squiggly lines than George Gazetas uses. He has different squigglies. Here's a power plant facility in South Carolina, not too far from Atlanta, Georgia. And in this case, we're going from soil in the very shallow part there up to very strong granitic rock. The shear wave velocity in the rock, these are two profiles done with a suspension logger, 3,078 meters per second. Wow, that's some strong stuff. That's the same as the shear wave velocity of steel. It has a fairly high uniaxial compressive strength. The unit weight, gamma, there's my Greek, 28 kilonewtons per cubic meter. And then we move to Rayleigh waves, again, also known as surface waves. There's some different acronyms for those. But we can put the sensors right on the surface of the ground at different spacing. That's what the different acronyms have to do with the spacing of the geophones and how we generate the wave in the ground. We can use an impact. We can use a vibratory source. We can use passive waves in the environment, such as little micro tremors or large construction equipment, train, rail, all generate some waves, vibrations in the ground. We put those to use. And we found out that we take the measurements in real time, but then we convert using fast Fourier transform to the frequency domain. And we found that high frequency waves are generated shallow, and then medium waves are in the middle, and low frequency waves are down deep. So by sorting out the waves by their frequency content, we could sort of build an approximate model with depth. So again, there's a number of different acronyms depending on the source of the waves and so forth. And I'll let you ponder this slide later because I'm sure there are another half a dozen new acronyms depending on some additional features that are out there. But these are the Rayleigh wave measurements. And here's what the equipment looks like. On the right-hand side, this is, I think, GDS equipment sells a commercial package for 30,000 euro. You get 6 little geophones on the surface and a little tiny shaker. That shaker's not very big, so I'm not sure you can get down very deep. On the left-hand side is Context system with 24 geophones, and here they're using an impact source. And they can go down pretty deep with that, even through pavements. And they end up with some dots that look like this. The dots are on the left-hand side, and they sort of develop a model. It's funny to set up 24 geophones. That takes about 20 minutes. And then they take literally a sledgehammer or a drop hammer in this case, and in less than 1 second, that's the event. All the data are collected in 1 second. It takes longer just to set up the geophones because most of them are wired. Although at Georgia Tech, we did purchase a wireless system, so you can have 24 wireless geophones. The setup's much faster. And then we build a model. Each analyzer would break that into different layers, and we can take that model and generate the orange curve on the left-hand side, and they play around with that for about 2 weeks till they match the dots with their model. And that's what takes so long to get the data out of these guys and gals. Okay, now here's a comparison in British Columbia, non-invasive geophysics with the Rayleigh waves as shown by the orange step profile, and then invasive geophysics, which is a downhole test, shown by the blue steps. See, they more or less agree. I think the steps make it look less agreement than they really are, but they sort of come together, and they're starting at, say, even less than 100 meters per second, which is pretty soft, increasing to about 220 meters per second at depth. And just as a point of reference to remember, if you can remember, Vs equals 180 meters per second. If the value is greater than that, it's good soil. If it's less than that, it's bad. There was a program by David Bohr and Ken Stokey some years ago where they went to 10 different sites and did downhole, invasive geophysics, suspension logging, which is another type of invasive, and then they did spectral analysis of surface waves at the surface, and you see the three colors of the dots. And more or less, they're showing agreement. They're going from, say, as low as 100 meters per second at the surface down to about maybe 650 meters per second at a depth of 100 meters. So we get similar answers, not the exact same answer, but very similar profiles. A more recent project called Inter-Pacific has to do with an acronym of their program. It's an international geophysics project. They looked at 3 sites in Europe, not too far from here: soft soils, stiff soils, bedrock, and they were doing this to compare what's called VS30. And they wanted to compare and see how the non-invasive compared with invasive methods. So it's all a blind study. That means no one knew the answers in advance. They had 6 teams on the invasive geophysics team and 14 on the non-invasive. And so here's where the sites are. I put Eurosize test here in Greece as a reference in case you're already familiar with that. And then we have the site Mirandola, which is the soft soil, Grenoble, which is the stiff soil, Cadarache, which is the bedrock site. So those are the 3 sites. Here's what the profiles look like. The soft soils on the left, Mirandola, Grenoble, stiff soil in the middle. Cadarache is mostly limestone bedrock. So Garofalo et al. 2016 A and B. I can recommend those 2 companion papers. Each of those papers has like 16 co-authors. And these are the kind of profiles. These are the invasive tests. They have done suspension logging with the purple squiggly lines, seismic dilatometer with the orange squiggly lines, downhole test with black lines, and the green are showing the crosshole test results. More or less in agreement at the 3 sites, fairly big range, as low as 100 meters per second on the left side up to maybe 2,700 meters per second on the far right-hand side. Pretty big range. And then here are the 14 non-invasive geophysics profiles using Rayleigh waves. So the invasive geophysics are all now represented by black squiggly lines, and the non-invasive are represented by orange squiggly lines. So you can see they're not the same answers, but they're all fairly close overall. There's a few exceptions. And again, I encourage you to read Garofalo et al. 2016 A and B. You can also put the geophones on what's called a streamer, which is a plastic sled, and one event, pull it over a meter, another event, pull it over a meter, and it goes very fast. You can say go 100 meters long in just maybe a couple of hours and generate a whole bunch of 1D profiles. So that's what these are. These are all a whole series. I forgot to count them up, but let's say 150 1D profiles side by side, and just plot them next to each other. Not much room for the mouse here. So they just plot these vertically next to each other. And it's interesting because if you remember, my reference point was what? VS 180 meters per second. What color is that over here on the scale? Anything less than 180 is blue, right? Blue. So you can just see the blue, you can just see where the bad ground is, all that area there on the right-hand side and the upper. So you can just see automatically where you've got a problem with settlements and or stability. You can even imagine if somebody was building a warehouse, the contour of the profile would be dipping down to the right. And because you have Gmax, you can actually calculate Gmax. You can actually start doing some calculations of that magnitude of that displacement. Here's something similar using passive Rayleigh waves, and they have looks to be rather karstic geology because of the way the profiles kind of come up and drop back down there. So red would be good. That would be some of the rock, and the blue's the alluvium, and then the green's filling that in between. So very valuable to have that kind of profile before you even start doing any drilling, any soundings whatsoever. And here's rather deep, going down 250 meters. This is NGI, Norwegian Geotechnical Institute, and they're using special seismic reflection profile with HH waves. They have developed a special source, and you can see the soils are in the upper profile here, and then here's the contour of the interface with the bedrock. Really impressive profile in Trondheim, Norway. We can have lab testing of shear wave velocity. These are the various methods. To do these, you have to have high quality undisturbed samples. That's always an issue with the lab rats. You have the highest quality. What kind of sampler did you use? Or we have field geophysics. I tried to put together a slide that showed all the methods that we've come up with to measure shear wave velocity. We have some creative people out there, and again, they all have their, if they don't have a TLA, they have an FLA, 4-letter acronym. Yeah, there's just too many of those acronyms floating around. But yeah, so we have a lot of different methods. They have some advantages and disadvantages to each of those, of course, but you do have that opportunity to choose. In fact, we have a whole series of international symposia now, probably a total of 14 volumes of technical proceedings, and the name of those symposia is Deformation, Characteristics of Geomaterials. The last one was held last month in Porto. So not only do we have lab rats and field mice, we have now geophysics represented by the fruit bat. Because fruit bats send out ultrasonic beep, 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 beep to find their food. Tasty food. It's not that tasty, but anyhow. So I think to be a great geoengineer in characterization now, you need to be a little bit of each of these little rodent type mammals. Now, I'm a big proponent of CPT. That's the one that I would normally choose most of the time to do my probing. It's much faster than soil borings. You can do 5 or 6 cone soundings at the same time it takes to do 1 soil boring to 100 feet, 30 meters. So we have cone tip resistance, pore pressure, sleeve friction, and we push the rods in the ground at a constant rate of 20 millimeters a second and take readings every second, so we get a lot of data. And these are some of the cones that we have at Georgia Tech. I have a complete selection of penetrometers from around the world. So the penetrometers are on the left, and then we have different vehicles for pushing those into the ground. You can see some are trucks, and some are track rigs, rubber-tired vehicles. So those are very interesting. And people that like the push cone penetration tests, we affectionately have a nickname for them, and they're called coneheads. So hopefully someday you will be appreciating the CPT, and maybe you already do, and you too can be a conehead. We also have an affectionate name for pressure meter tests. We call them a swell fella. And you're lucky because we have a special lecture on the Menard pressure meter at this conference. We also have the flat plate dilatometer, Marchetti dilatometer. And if you like that test, you are one of the knights of the blade. And you're lucky because we have a special lecture on the flat dilatometer too. And that also can be used to collect shear wave velocity. Geophysics, if that's what you really like, you are a freak, Nick. Freaky. That's a Star Trek picture there I stole. Or we could just put a geophone in the cone penetrometer, and as we're pushing it, we have to stop and regrip the rods every 1 meter. That takes about 15 seconds to regrip to start pushing again. And it only takes 100 milliseconds to send a wave from the surface down to the cone penetrometer. So if you are organized, which we are, then it takes us no more time to do seismic piezocone as it does to do cone or piezocone. So this is the minimum test that Georgia Tech will do, just because it was just so hard to get up in the morning at 0600 while you're going, you might as well collect shear wave velocity too. And here's a setup with the Indiana Department of Transportation. They're doing a seismic piezocone sounding. Here's the source right down here. And they push at the centroid. Push at the centroid. Sorry, the mouse is bigger than the spot to move that. Okay. And here's a sounding. These are where my students did this next to the University of Memphis. So they have red squiggly lines is the tip on the stress. Stress on the tip of the cone. Over here. Cyan is F sub S. That's the sleeve friction along the soil dragging along the cylinder up there. Here's the pore water pressure reading in blue. And then shear wave velocity every meter in brown. So we have 4 independent readings on soil behavior in a little sounding. The hole that we made is just 35 millimeters in diameter. It took us 3 hours to go 31.5 meters. And we have information about the strength of the material, the friction, the permeability, and the small strain stiffness. And I would say today, in 2023, you need that kind of information to do your job properly as a geoengineer. You need this information. Here's another example. This is in Charleston, South Carolina. This material is very calcareous. The calcite content is 60, 70, 80% below a depth of about 16 meters. So again, we have cone tip resistance in red, the sleeve friction in green, pore pressure in blue, and then brown for the shear wave velocity. And the shear wave velocities get up very high, over 450 meters per second. Here's a sounding going down 80 meters. Similar. It's fairly deep. Also in British Columbia, here's one that goes 140 meters deep. In fact, I have a soil boring next to it. The soil boring went 140 meters, and that cost 800,000 euro and took 11 days of continuous drilling. You have to keep drilling. You can't stop the drilling because the hole will close up. This sounding was right next to it and took 24 hours and cost 80,000 euro. 1/10 of the time and cost. If you can go deep. It's obviously geologic dependent. So we could do it the old-fashioned way. It's great. And I've had the pleasure of working on some large projects where I had literally unlimited amount of money to go out and do soil borings, take samples, do cross-hole tests, do standard penetration tests, vein shear tests in the clay, pressure meter testing to get modulus, packer tests to get permeability, all the lab tests I wanted. These were big projects that took 3, 4, 5 years, and I had literally several $1 million to do it. That's the conventional way. It's great. However, I still work more on small projects, medium projects. I still need numbers to keep me out of lawsuits, to keep the lawyers away, so I can do my job properly. So I'm recommending the seismic piezo cone with a seismic dilatometer because I can get 5 readings with depth from the same sounding. It's just an economical, efficient way to collect the data. And as soon as you finish the sounding, you have all the data. You can send that to the chief engineer back at the office. You can do the analysis as you're pushing the cone or the dilatometer. It's just fantastic. I don't have to wait 2 or 3, 4 weeks for the lab test to come in. I have the numbers now. Let's go forward. Here at the Atlanta airport, we went and we could collect the dissipation. It's sort of like a push-in piezometer. You can see when we hit the water table in my geology, the pore pressures go negative, almost cavitation, minus 95 kPa. But it doesn't desaturate it. All of these dissipations are coming up the hydrostatic, and if you follow the hydrostatic line back, it's right when the pore pressures went negative. And so I can measure the time it took to get T50, which is a dissipation rate, to get permeability. So in this case, I could do 5 independent readings with depth. 5 independent readings. There are some parameters that we can do to analyze the shear wave velocity and interpret here gamma. That's again my extent of my Greek speaking here. Gamma's unit weight. Well, it's also shear strain, but right now it's gamma T for total unit weight. There's a strong relationship with shear wave velocity, and this is the relationship we came up for soil. There's some simpler expressions, there's some more complex. And I eventually shared this with David Bohr, and he put that in his notes, if you go to his website, where he kind of matched that and put that together for rocks. Of course, cyclic liquefaction potential. You need the CSR, cyclic stress ratio. That's how much the ground's shaking during the earthquake. And you need a soil resistance. And that soil resistance is typically a normalized parameter from SPT, or CPT, DMT, or it could also be shear wave velocity, normalized shear wave velocity. So the idea is you know the level of the ground shaking, and if it's high enough and the soil resistance is low enough, you fall above a magic red line that's known as the cyclic resistance ratio, CRR. And in that case, liquefaction is likely, or you're far enough away from the epicenter, the level of shaking is much lower, and or the ground is stronger, and you fall on the underside of that red line, CRR, and liquefaction's not likely. I mean, that's how it was handed out to us by Harry Seed some years ago, and people have used it. Was originally done on relative density on lab samples, but you can measure or infer the relative density from SPT, CPT, DMT, shear wave velocity. How do we get that? Well, it's probably a simple shear mode, but essentially the cyclic stress ratio is a normalized shear stress. Cyclic shear stress over the initial effect of vertical stress, and I think you know that already from George Gazetas' work. So you can put the layers in there, and to do that, you need shear wave velocity to get G max for each of those layers. How do you get the cyclic stress ratio? Well, you can do a linear elastic method. There's a number of programs for that. I can recommend Youssef Hashash, who's a professor at University of Illinois, Urbana-Champaign. He developed a model called deep soil. Or you can do nonlinear ground response methods. Same thing. I can recommend deep soil. 1, it's free. 2, it's a fairly recent program, and so you can go either way. And there's the link for the website. You do have to register, so that in case there's any bugs in the future, Professor Hashash can notify you and update you with the latest version. So that gives you the value on the y-axis. And then on the bottom here, we have normalized shear wave velocity called VS1, which is VS over the square root of the effective vertical stress in bars, although there are other ways of normalizing that. I don't have time to cover that day, but there's the CRRs for different fines content of soil. You see there's not a huge effect, but this is the original Andrus and Stokey relationship that's published by Les Yount et al. In the Journal of Geotechnical and Geoenvironmental Engineering. And that was more recently updated by Robert Cahan et al., where they added 301 new case studies. And instead of just a binary decision, yes or no, they put in the probability of liquefaction going from, say, 5% to 95%. You can also look at VS30, which is sort of the average. It's not really an average shear wave velocity because it's really the average slowness. Slowness is the reciprocal of shear wave velocity. But this is how you would calculate that. And with that, you could go to, say, an international building code where they would put you in different seismic site classifications. I'm sure you're familiar with that because of your geology here in Greece. We could also look at some direct correlations. Say, here's a correlation of shear wave velocity with cone tip resistance. And I put in here George Gazetas' relationship that he had in soils and foundations. And I think it matches the data from Michael Long, University College Dublin. George was saying shear wave velocity in meters per second can be estimated as 150 times the square root of cone tip resistance in megapascals. You can relate the undrained shear strength to shear wave velocity, and this is for the simple shear mode. You see the data on the right, different colored dot, different symbol for each of those clays. And it's just an approximation. I think it's probably best not done just by itself, but if you had to get a quick estimate of the DSS undrained shear strength, here's one way to do it. In fact, I pulled together, compressive strength and the shear wave velocity of rocks. And so we have a number of different kinds of rocks here. I guess I'm missing the one. Yeah, lost a figure, but that's okay. So here's the uniaxial compressive strength with shear wave velocity. We also had two databases of clays, one where the clays were anisotropically consolidated before shear, so CAUC, and another where they're isotropically consolidated because that's a much easier test. What's interesting, there wasn't much difference in the answers, but in all three of those regressions, what I found interesting was the exponent was always 1.3. So you can see there's a discontinuity as you get up in the clays, as you transition from soft clay to firm clay, stiff clay to hard clay to now fissured clays are going to jump up, as would rocks, because they're mostly got discontinuities, cracks and fissures. So there's a step up there. They shouldn't be tied together directly. But you see the transitions. We go from, I guess we added in some Cooper marl and some Dublin boulder clay just because they have fairly high shear wave velocities for very hard clays. You can look at pre-consolidation stress, and here this is modified after a paper I did with Peter Robertson and Tom Loney. But as a first order estimate, if the clay is intact, the pre-consolidation in atmospheres is given by this simple equation. And again, you can see the step up. If you have a fissured clay, it's in this ellipse up here. Again, fissured clays have a whole network of cracks and fissures, depending on how they got heavily over-consolidated. And just a point of interest, London clay, I guess, has experienced 200 to 300 meters of erosion. You start looking at some of the older clays like Oxford, and it's even more than that. You can look at the pre-consolidation of sands, yield stress, pre-consolidation versus shear wave velocity. So we have the shear wave velocity, and it's the max, G max. We could convert that to an equivalent Young's modulus. And sometimes that's going to be too stiff. That's the maximum stiff, so it's a great reference point, but probably we've developed some shear straining. So we have static reduction curves, and we have cyclic or dynamic. And so here are, say, the famous ones from Hardin and Drenovich, Husetic and Dobry, where G over G max is the modulus reduction curve for cyclic loading versus shear strain. Here's a more recent set, 26 plays by Vardanaga and Bolton, 2013. And what's interesting about their method is they could take their method and apply it to static loading. You see the exponent H up there on the left upper curve, as well as this factor JP, which is shown inside the curve. So they have a method that applies to both monotonic, static loading, and dynamic loading. We do a lot of work with monotonic loading because we want to apply this to static loaded like foundations, shallow foundations, and deep foundations. So instead of using shear strain, log shear strain actually, we use mobilized strength, tau over tau max. You're just entering the stress strain curve from the y-axis instead of the x-axis. Or Q over Q max, which is essentially 1 over the factor of safety. So on any project, I have to calculate factor of safety anyhow. So I could use that to get my modulus reduction factor. And so here we've got data from sands and clays, torsional shear and triaxial. So we start out with, say, resonant column, get the G max, and then we use torsional shear to shear statically to failure. That would be represented by a factor of safety of 1. And so here's an example. This is soft clay in Burstwood, Australia. It's one of the national test sites. And I use the shear wave velocity to get the beginning of the stress strain curve. I use the cone tip and pore pressure to get the strength, and then that algorithm to tie it in. So the lines represent my synthetic stress strain strength curves from the seismic cone, and the dots are what they actually measured by the PhD student at the University of Western Australia. And I think that's a pretty good match at all those different depths. You do the same thing for sand. This happens to be special frozen sand samples from Charleston, South Carolina. And the red dashed lines on the right-hand side are the estimated stress strain strength curves using the seismic cone. And the dots are what they actually measured on the samples when they were brought back to the lab, thawed out, and then tested in triaxial compression. And again, I think they did a good job matching those. We can apply that to, say, pile foundations. This is the simple solution, but obviously there's compressible pile solution. I take the cone data, and I can use the cone tip, pore pressure, sleeve friction to get the capacity of the pile, and I use shear wave velocity to give my modulus, and then I can calculate the displacement at the top of the pile, and I can calculate the load transferred to the bottom of the pile. And so here's an example from Georgia. This is a site about 45 minutes south of Atlanta. It's an interstate I-85. You see there's a cone truck, and I have a drill shaft foundation with the dimensions shown in the lower right. Here's the seismic piezo cone that we did at that site. Red squiggly lines, the orange and the blue are used to get the capacity of the pile. And then the shear wave velocity gives me the stiffness along the side of the pile. And now I can compare the lines. The top down loading is purple, and that should match the purple dots. And the red is the shaft response, how much load went into the side friction. And blue is how much load went to the base of the pile. And we all know from kindergarten that blue plus red equals purple. Yeah, blue plus red equals purple. We learned that in kindergarten. Go back and check your notes. Go back and get your notes from kindergarten. So I think that's a good match there. We published that, of course. If you're looking to do finite elements, some people use Plaxis in the United States. FLAC is fairly popular. Soil Vision 3D, you can do that. We also have seismic dilatometer. And seismic dilatometer worked in Venice with the Marchetti family. We said, hey, we got to stop every 20 centimeters to get A reading and B reading. Let's get the shear wave velocity. We're there already. What's going to cost us to do it? So we did that. We call that frequent interval shear wave. And so you see the dots. We have way more dots than you normally get. I superposed the steps that are 1 meter. Again, I think that's artificial. But soil really does have a shear wave profile that's just as developed as any other reading that you would push in the ground. So we call that frequent interval. You get a lot more wavelets to follow. Some people call that the cascade, waterfall cascade. Here, that's the shear wave velocity. Here's another example of at Lake Michigan at the Northwestern University test site. The blue on the right-hand side, the blue steps are the traditional 1 meter steps. But you can do a better profile if you do it every 0.1 meter. Why not? You're there. It's just better definition of the profile. And here's one at Savannah Riverside. You see very detailed, going down about 45 meters. Much more detail in the shear wave than you usually get. You can also do continuous. I said you could get the auto size going 1 whack a second. Whack, whack, whack. So here we're down in Brisbane, Australia. There's that yellow box is the auto size. It's a fairly big truck on a little tiny box like that. But there's the profile. This happens to be a profile in Norfolk, Virginia. You see the paste up, the cascade, if you will. They're very clear. What's also interesting is to see how in the softer material, it's much smoother in the noise coming up to the shear wave. And then in this lower formation, which has calcareous components, it's much noisier. So you can almost just use the pre-arrival of the shear wave to tell you what kind of soil type you're in. Anyhow, here's the regular interpretation, crossover, peak, cross-correlation, spectral analysis, get slightly different answers. And here's the continuous, where we're just delivering a wavelet every 1 second. And here's the total profile. So you have cone tip, you have sleeve friction, you have pore pressure, and now you have continuous shear wave velocity. It's just another reading. Here we're going down 45 meters in Richmond, British Columbia. There's the waterfall. Again, you can tell the soil type, 9 meters of soft silt, sand down to about 30 meters, and then soft clay below 30 meters. So the pre-arrival is telling you what kind of soil you're in. I think that's very interesting. But then if you process the shear wave velocity continuous, it does a very nice job matching the traditional stop every 1 meter and do that. So, you know, as I put these slides together, I said, geez, what's my legacy going to be for the Athenian lectures? Because there's been so many great people before me. Is it that I'm the first musician to give the lecture? No, because Harry Poulos gave the first Athenian lecture, and he's a guitar player. He's a great blues guitar player. So I played at his house. He's played at my house. Yeah, it's fun playing music too. We call it geo-music. Am I the first to discuss soil behavior? No, that would be John Berlin, 6th Athenian lecture, 2010, and we both share a common interest in critical state soil mechanics, for sure. Is the first to be a rock star? No, that would be Nick Barton when he gave the 8th Athenian lecture. You know, he showed a book he already published. Here's another book. I mean, he developed the Q system, the rating for rock masses. Just awesome. The first to discuss soil dynamics and earthquake engineering. No, that's not me. That's Professor George Gazides, 3rd Athenian lecture, 2004. Yeah. So I think my legacy is going to be that I'm the shortest person to ever give the lecture. Yeah. Epadisto.